Hello everybody, welcome back to another structural analysis video, and this video is going to be on the moment area theorem. This is a pretty tricky concept, so this might be split up into two videos, for theory and one for problem solving. But just for now, I wanted to make sure that we all get a good understanding of what the theory is and why we even need to use this in the first place. So pretty much the moment area method is a theory or a method of structural analysis that allows us to determine the deflection and the slope of a complex beam configuration. Now, in our textbooks, we normally have simple configurations for things like simple beams or cantilevers and things like that already have formulas derived so that we can solve for these slopes and deflections at specific points. However, in the real world, we usually have beams that are random configurations that cannot be simply solved just from one formula in a textbook. So we need to go to analysis methods, and one of those is the moment area theory. And one of the critical components of the moment area theory is knowing about the elastic curve. This is a critical concept because it allows us to predict the structure's deformation upon loading. So in this case here, we have a fixed pin situation with a point load, and we can predict that there's going to be a deformation as follows with this blue line here. And for any given point on this elastic curve, we can actually take out a specified deflection represented by V or a slope represented by theta for any given point. Now, this deflection depends on different beam properties, like its geometry or its support conditions, but most importantly, the flexural rigidity is a big role in what defines the maximum deflection for a beam, or the magnitude of that deflection. And we recall that the I, which is the moment of inertia, is simply the section's resistance to bending. And the E, or the modulus elasticity, is the relationship between the stress applied to the strain developed. Now, why is this important? This is important because we are going to be looking at the beam in its elastic phase so that we can use its elastic curve to predict the deflection of the member. Now, what the elastic phase means, obviously, is that no yielding has occurred yet. Okay, so all of this is just to preface what the theory for this structural analysis method actually covers. And the first theorem of this method was actually derived by a person named Charles Green. And pretty much what he related was that the change in slope for a segment of our beam with respect to the elastic curve will equal to the area under the M over EI diagram between the points of the segment. Now, if we relate this to a point-to-point condition, so from A to B, instead of relating it to a segment, we can then take the area of the M over EI diagram between these 2 points and solve for the slope between those 2 points. And in order to visualize this, we're going to be using some tangents from those 2 points. So we have a tangent extending from point A and a tangent extending from point B. And we can see that the angle created between these two tangents will be the slope that we're concerned with for those 2 points. Now, tangents are going to be a huge part of this theory, which we're also going to see in the next part of the theorem as well. But this is the first theorem derived, and it's represented by this formula here. Now, the second theorem is going to be relating similar concepts relating to points in the M over EI diagram, but instead this time we're going to be looking at the change in deflection between 2 points. But first, if we looked at a segment, the relationship says that if we take this segment and we take the change in slope times the distance between the point with respect to the distance to the segment that we're looking at, we can actually solve for the change in deflection for that segment. Now, in a similar way, if we plug in the area under the M over EI curve, because we already solved that the change in deflection will equal that, we can plug that in and then use that in our formula. And then once again, going to a point-to-point basis, if we consider from point A to point B, we have to figure out what this x is. And since x before was going from point A to the segment, we are now going to be considering A to the centroid of the M over EI diagram. And that leaves us with our final formula, for t over AB, which is simply the tangent extension or the deviation from point A on the elastic curve to the intersection of the tangent extended from point B. Simple as that, right? So with respect to A to B, we have this tangent deviation TBA. And similarly, from B to A, we have TAB. And these lengths are going to be super useful in finding the deflection for specified points. And that's pretty much it for the theory. It's a little bit complicated without seeing a problem, but to get into the problem, we need to look at the procedure. The first thing we need to do is get that M over EI diagram that we've been talking about so much. We have to predict an elastic curve, and then we apply our theorems to the problem. So let's hop into that problem and see what we're dealing with. Alrighty, so here's the problem, and here is the beam configuration that we're dealing with. And the problem is asking us to use the moment area theorems to find the slope and deflection at point C, which is at the end. And it is telling us that I is varying throughout the member. And all that means is that as we go down the length of this member, we are going from a uniform moment of inertia value, and then we are tripling that value with respect to this segment, and then quadrupling that value with respect to this segment. And we'll see how that influences our formulas as we go through the problem. But as we mentioned, the first thing we need to do is fill in this M over EI diagram, and we're following basic procedure as we've done previously. So we need to first get these reactions at A and B, and a simple way to do so would be to take the moment about A, which will equal to 0, write down our sign convention, and then start filling in for what we have. And we have this first reaction here, which is going to be creating a clockwise movement, and that is 15 meters away from A. Following that, we have BY, which is going to be creating a counterclockwise movement 20 meters away from A, and we have that negative 400 at C. 15 plus 5 plus 10, that leaves us with 30. And solving for that, we can get our first variable, which is by. And that's going to be 750 in the positive direction. This is in kilonewtons. Now we can simply solve for the summation of forces at y equals to 0. And we only have to solve for ay, which is the last unknown here. So we have ay minus that 200 at point D. We have the by, which we solved for, and we have the negative 400 at point C. Solving for ay, we are left with 1,005 or 150 kilonewtons, sorry, and that's going to be negative. Now we can move on to plugging this in for our shear and moment values. Alrighty, so now that everything's plugged in, we just solved this basically with our previous understanding of shear and moment diagrams. So if you need to recall on that, feel free to go back to previous videos. But for now, we're talking about the good stuff, which is the M over EI diagram, which is brand new. And we notice that we have this integral here for both of these formulas, meaning that we actually need to consider the area of these moment diagram segments. And another important thing about these areas is that if we considered a triangular shape versus a rectangular shape, they're going to have different centroids, which is going to be important for this tangent formula or this tangent deviation, because this x value is going from a specific point to the centroid of these areas. Okay, so the first segment here is going to be representing this triangular bit for the uniform inertia value. Okay, and we know that this area will have to represent 1/2, and we have a length value times the total magnitude at the top of this triangle. So we have a negative 2,250, multiplying that times the length of 15 for that segment, and that's all over EI, which will leave us with 16,875 over EI, and that's going to be negative. Now let's do a rectangular section here. We're going to have a very similar thing. We are taking a 2,000 negative 250 times the length of 5. And this is different because now our segment has 3 EI, so we have to put that over 3 EI down here. And if we simplify this formula, removing that 3, we will be left with 3,750 over EI. And I'll do the same thing for segment 3 and segment 4, and you can check the values after. Alrighty, so now that we've solved for segment 3 and segment 4, you'll notice the only differences are we are now taking the difference between 4,000 and 2,250 so that we can get this area alone for segment 3. And then for segment 4, we have to consider that 4i since we are switching to a segment that has a larger moment of inertia. Now let's draw this on the diagram and see what we need to do next. Alrighty, so now that we have it plugged into our M over EI diagram, we can see what we were actually solving for was these resultants at the centroid of these segments. And this is going to be important because later on we will solve for these distances with respect to that centroid to a certain point of reference to get these tangents and slopes. Another important visual thing here is to notice that the segments actually appear smaller on this diagram because they are now considering the flexural rigidity with respect to the moment acting at a segment. And the greater your flexural rigidity is, the less influence the moment will have uh, with respect to deflection and slope. And now we can actually hop into the rest of the problem, which is the fun part where we're identifying that elastic curve and drawing these tangents and slopes. Okay, so let's hop into that part.